In this video, we're going to finish working through example 3 that we had started last time. So we're still dealing with these same three uniform fields, P, Q, and R, as I have on the screen now, except now we're going to work through parts 4 through 6. So in the last video, we did parts 1 through 3. Now we're going to focus on parts 4 through 6. So let's start with part 4 here. Okay, so let's go to a new page. Let's paste that, get rid of this guy. All right, so here we see we have two cross products. We want to do Q cross R first, and then we want to cross that with P. Well, there's an easier way to do this than doing all two of those cross products. So we can do cross product twice, or we can use that back cab rule, because we recognize that this is a vector triple product. And so what we can do with our back cab rule is, instead of doing all these cross products, we can essentially just do dot products, multiply vectors by scalars, and then vector subtraction. So let's go ahead and write what this is equal to. Actually, let me take this down here so we have some more room to continue it. So let's bring this here. And let's go ahead and sort of assign in our heads, and let's write it out here. But of course, in our back cab rule, we have A, B, C. So in this case, our P is like our A, our Q is like our B, and our R is like our C. So with that in mind, we can write that this vector triple product is equal to back cab, so BAC, in this case our B is like Q, times the dot product of A dot with C, so P dot R. And then cab, so we subtract. C corresponds to R in this case, and that's multiplied by our AB, so that's going to be P dot Q. So now we can evaluate the right-hand side of this equation, and that's going to be a lot easier generally than doing two cross products. But again, that's personal preference. If maybe you like doing cross products better, you can definitely do that. In this case, I'm going to kind of show all of the steps, so it might seem like this is a little longer, but of course you can skip some of these or not write them, or even do them in your head in some cases. So again, I'm just going to write our values. So for instance, for Q, we had 2, -1, and 2, and so you can look at the notes in Canvas or go to the previous time in the video. And then for our P dot R, we have our P was 2, 0, -1, and we're dotting that with our R, which is 2, -3, 1. Okay, so that's our first term. Now we're subtracting from that. We have 2, -3, 1 for our R, which is being multiplied by the dot product of 2, 0, -1, dotted with 2, -1, 2. So I'm kind of running out of space here. That should be an angle bracket to close that last vector there. So now well, I'll go ahead and write all of this out just so we can see it. So we still have this 2, -1, 2 out front. So let's go ahead and do this dot product. So again, for dot products, remember we're going to multiply 2 by 2, and then add to that 0 times -3, and add to that -1 times 1. So what we get from that is we get 4 plus 0 plus -1. And of course, that's ultimately just going to be a scalar number resulting from our dot product. Then we have 2, -3, 1. And then for our dot product here, we have 2 times 2 plus 0 times -1 plus -1 times 2. So from that, we have 4 plus 0 plus a -2. So what this becomes then is 2, -1, 2 multiplied by a scalar. This first one is just going to be 3, and then minus our 2, -3, 1 multiplied by a scalar, which is just going to be 2. For scalar multiplication, we're just going to multiply each component by that scalar that's being multiplied. So for instance, we have for this first term 6, -3, 6, and for our second term we're just multiplying everything by that 2, so we have 4, -6, and 2. And then finally we can do our subtraction, and I'm going to write this in terms of our unit vectors. So we have 6 minus 4, which is 2 in our x direction, negative 3 minus negative 6, which is going to be a positive 3 in our y direction. And then we have 6 minus 2, which is going to be 4 in our z direction. And so that would be our answer for part 4. Okay, so moving on to our next part. So here we want to find a unit vector that's perpendicular to both q and r. All right, so where are we even going to start with this? So this isn't the same as our other parts in that we're not explicitly told what operation to do. So again, maybe pause the video and try to work through this, try to figure out maybe at least where do we start on this problem. So there is an operation that we have talked about that we can use to get this answer. We know that both q cross r and r cross q are going to result in a vector that's perpendicular to both q and r. So let's just say this results in a vector. So of course cross product gives us a vector, and in this case is going to be perpendicular to both our q and our r vectors. Okay, and of course both of these, so they're just going to be in the opposite direction. So if we think about the plane being sort of on a sheet of paper on a desk in front of us, one is going to be coming up, one is going to be going down. So just opposite directions, and we'll see that in the math here in a little bit. So let's just go ahead and choose one arbitrarily. We can say let's go with this q cross r. So we need to evaluate q cross r. So again, we're going to do our 3 by 3 determinant. We have our unit vectors ux, uy, and uz in our first row, q in our second row, so that has 2 for x component, negative 1 for y, 2 for z, and then r in our third row, 2 for x component, negative 3 for y component, and 1 for z component. If we evaluate that, we see that this is going to be equal to, let me actually come down to this next row just so we have enough space. So we're going to have negative 1 minus a negative 6 in our x direction, minus 2 minus 4 in our y direction, plus negative 6 minus a negative 2 in our z direction. And again, if you have any questions about how to find those numbers, please let me know. But we can also do this in MATLAB or in some calculators as well. So what we get from this, negative 1 minus a negative 6 becomes 5 in our x direction, minus the 2 minus 4 becomes plus 2 in our y direction. And then finally, negative 6 minus a negative 2 becomes minus 4 in our z direction. So now we have this vector q cross r, which we know is perpendicular to both q and r. However, we go back to the problem statement and we see that we actually want a unit vector. So just by glancing at this, we can see that the magnitude of this vector q cross r is going to be greater than 1, so it's not a unit vector. So we need to figure out how to do that. One thing to note real quick before we do that, again, we said that r cross q is just the negative of q cross r, so if we wanted to, let me just sort of put down here as a note, so r cross q we could say is equal to negative 5, negative 2, plus 4. And we could use that if we want as well. But let's stick with this q cross r for now. So because we want a unit vector, we're going to use our definition for the unit vector, and we say a unit vector is going to equal to this vector q cross r. Of course, if we wanted, we could introduce a new variable. We could call this vector b, vector w, whatever we want. But let's just call it q cross r for now, divided by the magnitude of q cross r. So plugging in values. So of course our vector was just 5 to negative 4. And then the magnitude, by definition in Cartesian coordinates, is going to be the square root of each of those components squared. So square root of 5 squared plus 2 squared plus negative 4 squared. Okay, so if we evaluate that, we get our desired unit vector. So that is equal to 0.745, and so this is approximately in our x direction plus 0.298 in our y direction minus 0.596 in our z direction. And so that's going to be the answer for part 5. Now there are a couple things that we can do to check this. If we want to check the answer, of course, we could find the magnitude of that unit vector, and we know that it should be equal to 1. If you have some approximate numbers like this, using stored numbers in the calculator will give you exactly 1, but if you're not using stored numbers, you might just get something really close like 0.9998 or something. Another thing that we need to check is we know we want this to be perpendicular to both Q and R, so how could we check that? Well, we can check that with our dot product. So we could do U cross Q, and we could do U cross R, and these two should both be equal to another, and they should both be equal to 0. And the reason for that is because, remember, our dot product has that cosine theta term in there, and if they're perpendicular, our theta is equal to 90, and of course, cosine of 90 is 0. Okay, one more part to go here. So for part 6, let's come all the way back up here and bring this down. So we want the component of P along Q. So we're dealing with a projection here. Okay, so let's come down to a new page. All right, so it looks like I didn't quite copy that. So let me try one more time here. All right, so we want the component of P along Q. Okay, and again, we're dealing with projection. So we can go back to the definition that we had before. And so our projection of P onto Q, or our component of P along Q, notation-wise, we said is P sub Q. And we said that is equal to, we have our P dotted with a unit vector in the Q direction, but that's a scalar value. And remember, we wanted a vector. So we said if we multiply that by that unit vector in the Q direction, that gives us what we want. So from this, we can see that we need to figure out what this unit vector in the Q direction is before we can do anything. So let's go ahead and find out what that is. So our unit vector in the Q direction is, again, by definition, just going to be Q divided by the magnitude of Q. So plugging in the values given for Q, we know that Q is 2, -1, 2, and our magnitude is going to be the square root of 2 squared plus -1 squared plus 2 squared. So we get something that looks like that. So if I plug this in, I get that this is 0.6 repeating in the x direction minus 0.3 repeating in the y direction, and then we have a positive 0.6 repeating in our z direction. Okay, so now all I need to do is plug into this equation here. And so I can say P projected onto Q is equal to our P vector, which is 2, 0, -1. And then we're taking the dot product of that with our unit vector in the Q direction. So 0.6 repeating, -0.3 repeating, and 0.6 repeating. And then we're multiplying that result by that same unit vector. So 0.6 repeating, -0.3 repeating, and 0.6 repeating. So again, I'm not going to write out sort of the intermediate steps, but basically what we would do is we would have 2 times 0.6 plus 0 times -0.3 plus -1 times 0.6. So all of that is going to result in a scalar value. We're then multiplying that scalar value by each one of these 3 terms here. So we're going to have an x, y, and z component. So if I use those exact values of 0.6 repeating, 0.3 repeating, and 0.6 repeating, the final answer is our projection of P onto Q, or our component of P along Q, both mean the same thing, is equal to 0.4 repeating in our x direction minus 0.2 repeating in our y direction plus 0.4 repeating in our z direction. And that would be our answer for this part. So that covers our unit on vector algebra. Hopefully you feel comfortable with that. Again, remember, we want to have a good basis in this moving forward. If you have any uncertainties, definitely let me know. In our next unit, we're going to be moving on to talking about different coordinate systems.